Hello, welcome back to our tutorial. So this one is actually what we have done in last week. In the last tutorial, we play around with the optical flow and the use of optical flow to move virtual objects on screen. So that is what we have done so far. In today's video, we would like to enhance this one not only by using our gesture to move the ball, we would also like to rotate the ball by using our fingers or other part of our bodily movement. So let's see how we can modify this one for the rotational effect. So in order to work with, you need to download what we have done in the last tutorial, that is this piece of work. So if you remember that we have this flow move component that you can specify the radius, that the size of the circle, together with an initialized button. And in order to have a look at the rotational effect, we might also want to modify a little bit of the texture pattern such that it's a bit more visible by adding like a text into here. So I use the default Arial font and make it bigger with the text around here, and then we can add a composite. To put the text on top of the noise pattern such that we can have this one. And then the next step, if you want to, you can also make the ball a little bit bigger such that we can easily manipulate the rotational effect. Okay, and then let us take a look again what inside the flow move component. So we have defined the circle in a three-dimensional space and using the parallel projection onto the render top, and then eventually send out to the output top. And then the majority of the computation is done by this class ball that we explained very thoroughly in the last tutorial. So we are now ready to add in the rotation. So for the rotation, in order to separate it from the main calculation, again we can add a constant with the name angle and add it to a null, and that one we can call rotation. So eventually we'll modify this angle by the calculation that we are going to do, and the rotation will go to the geometry in the Z direction, because rotating in the 2D screen is only like visible in the Z direction. So we're going to send this to the rotation Z. So if you would like to test, for example, if you rotate it like 45 degrees, so the result will be something like this one. So we would like to do it interactively such that the degree will, the angle will change according to our movement. And the second thing we might want to change a little bit in the ball class definition is the velocity. And if you remember that velocity will add to the existing velocity by using the change of the optical flow information in x and y direction as shown in here. So that will be kind of like accumulate. So in that case, you will see the movement will have its own something like acceleration. And but for this effect, is might be a little bit to manipulate the rotation because it will escape from your hands immediately. So in that case, probably we want to just assign the velocity directly to the velocity variable such that it will not escape from your movement. So that is something we would like to do. So remember to initialize again. Okay, so in that case, the ball will actually follow your hand movement and it will not immediately escape. If you just for example, pat it on the right hand side, it will not just go directly to the left margin and then bouncing back. So that will be a little bit easier for us in case we want to rotate it. Okay, so to start with the rotation, so everything we need to do is to just change this constant. And the information that we have for the rotation again is from the cropped optical flow information. So this is the optical flow that if we move our body, that's the optical flow information. So that will be the only input. So what we are going to do is to add a component in order to isolate this piece of information from here. So we can call it flow rotate, ROT, and then the input will be the only optical flow information that we obtain from outside. And then the output will be actually a chop. Then we're going to send out the angle that we are going to rotate the object from our hand movements. So in this case, we need to connect this one first. So we have our cropped optical flow information, and then eventually the angle will send out to this null chop to form the rotation parameter. Okay, so that is the configuration. And how we are going to find out that one, that can be a little bit complex. So let us look at the explanation. I put it in the page one. So in order to compute the rotation, what we would like to do is to take every pixel from the optical flow information, say point 1 and point 2, to see which direction of the optical flow is going to. And in order to rotate this virtual ball, so we might want to compute, for example, this vectors for P1 and also P2, which is something like a tangent along this particular line connecting P1 to the center of the ball and also connecting P2 to the center. So when we compute this particular projection onto the tangent and then we average this, or we sum up all of them, and then we can determine whether this ball is rotating in clockwise or anti-clockwise direction. For this example, is in anti-clockwise direction, and this angle of rotation is actually depending on the length of those vectors we add up together. So that is the basic logic. And in order to compute the length and also the direction of this two or more vectors. So we need to do something a little bit more complex. So let's say Cx and Cy is the center of the ball right here. And then x1 and y1 is the point over here. And in the next frame, if we detect the optical flow in x2 and y2, that the movement of my finger or hand is in this direction. So in that case, we would like to take the projection of this vector x1, y1 to x2, y2 onto this tangent line, that is x3, y3, which form a right angle to the line connecting x1, y1 to the center. So to compute the length and also this direction, so we might need to find out this angle we call A4. So in this case, we need to find out A1, which is this angle. That can be easy because we know x1, y1, this point, and also the center. We do an arctangent to find this one. And the second angle we have is A3, which is the angle between the x2, y2 and x1, y1 along the x-axis, horizontal axis. That is the A3. So we know this point and we all know this point. We can do an arctangent again to find the A3. So A3 minus A1, A1 is also this one according to our high school geometry. So we A3 minus A1, we can compute this angle. And since this one is a right angle 90 degree and we minus this angle, actually we come up with A4. So that is this formula, 90 degree minus A3 minus A1. And the length of this vector perpendicular to this line connecting to the center is actually the length of this diagonal, D2. And then we take the cosine of the A4 that we find this one. So we might also assume that the rotational string, that's the force along P1, should be larger than the effect of P2 because the distance between P1 to the center is much longer than P2 to the center. So this is again our intuitive ideas about something like the lever, that we have a greater distance, that the same amounts of the force actually produce greater rotational strength. So that is our idea. So in this case, we need to find the length of D1, the length of D2, and the angle A4 to compute the rotational strings, and for each of the point in the bounding box like this one. And to compute the length of D1, that is from the bounding box any points over here towards the center of the ball. So we try to use this formula, that is how we compute the magnitude, that's distance between a point, actually between 2 points. One is the center, and normally the center we call it 0, 0, so that is the easy way to do so. And then to compute this angle, we call it arctangent. So that is the basic formula we learned in high school. And then for this computation, there are two ways to do so. One, you can do it in a chop by using each of the point as a sample and then to do the calculation. And the other way that you can do is the top mathematics that would be probably learned from the very famous YouTuber Packata that he used quite a lot in his channel. So we are going to use similar approach to use a top for this computation. And so this is the explanation I will go through in the video in a moment that how we can come up with the idea of the distance and the angle by using this kind of RAM calculation. Okay, so let's start with the wheel thing here. So we are going to do the calculation. The first thing we are going to do is to calculate the distance that I show you around here. So this bounding box is actually the size of the ball, and we calculate the optical flow around here. So in order to calculate the distance between any point towards the center, we would like to do it with the RAM mathematics, like this one. So we will set up a RAM, one horizontally corresponding to the X, and the other I change it to vertical corresponding to the Y, and the size of this RAM should be the same as the bounding box of your virtual ball. So I can just obtain this one by using an info chart. That is 96 by 96 pixels. So this is the resolution X and resolution Y. So I can do the selection to choose the res X and res Y, and then just customize the input, sorry, the resolution here. Okay, so I export chop, so just in case I may change the size of my virtual ball. Okay, and the other thing that we would like to do is to customize the output format using 32-bit for the calculation, and also just single channel. Yes, so that is the first part. And if you would like to take a look of the pixel value, so you can turn it on so you can see this between 0 to 1. But I would like to have the 0 in the center, the negative on the left hand side and the bottom side, in order to let it reflect this particular situation. CXCY is the origin, 0 here, and this negative right here, positive right here. So in that case, I can do mathematics calculation. So I can just minus 0.5 for each of them. So for the pixel value, again, you can also have a look. So the left hand side around minus 0.5, center will be close to 0, and then the right hand side will be positive 0.5, and again single channel 32-bit. And then the next thing we would like to do is to merge two of them. So the first one I put and first input and then the second input. So the output red channel, I take the input one, that's the x coordination horizontal. I take the, actually it doesn't matter, I take the luminance. And the second one is input 2, I also take the luminance. The important thing will be the output format. This 32-bit, but with just 2 channels, red and green. Oh. Yes, I take the red and green. So in this example, you can also want to see the pixel value right here. So the R and G come with value, and then the positive 0.5 around here, negative 0.5 around here. So that's what we want. So based on this one, we can actually go back here to compute the distance and also the angle. Since we would like to compute the distance and angle of this fixed circle, and at the same time we also want to compute it in our variable optical flow data. So in this case, it would be good for us to put the computation of the magnitude, that's the distance, and also the angle in two separate components such that we can reuse them later. So in that case, I also add one with the name like magnitude. And another one with name called angle. Okay, so for the magnitude, we're going to input this one, and in this case we have another input top, and the output top will again be another out top. So this one go to here. And how we're going to compute the magnitude? So we go back to this calculation. It's actually we take the square of this distance, that is here, the py minus cxcy. So cxcy is actually 0. So in this case, we just take pxpy square and then plus the py square, and then we add them and then take the square root, and then we'll compute the distance for every point along this bounding box. So it's pretty straightforward. So we're going to do a math. The math is channel pre-operation, that's before the calculation we take the square. And if we take the square, actually you can see that is a little bit more symmetry. There's no difference between the positive and negative side. And then we combine the channel by adding them together. But we only have 2 channels, so the input will have 2. Then output we're going to have just one single channel. So the output will be 32-bit mono. Just keep one channel. So that is the result before taking the square root. So you can also have a look to close to the center with 0, and then there will be greater towards the margin. And then the next step is we're going to take the square root. So square root we cannot do it in math, but you can do it in function. With the function we do just the red channel, we can do the square root. So the square root afterward we are again using single channel mixture. Yes, we just keep the red channel. So now you have the square root value, which essentially is the distance between each of the pixel towards the center. So the center will be 0, of course, and then there will be greater value towards the margin. So now we have the magnitude value. Okay, so this one is done, and then the other we're going to calculate the angle. And again, taking in this two channel RAM information. So we have the input and also output as top. For calculation of the arctangent, we also have a function. So in here, so when we do the calculation, we can do something called arctangent 2, because arctangent 2 is the one accepting two input 1 and input 2. Input 1 is the x direction, y is the vertical direction, so we can send it to input 1 and 2. And if we do the arctangent without 2, you need to do the division first, but somehow we may encounter division by 0 in this case. So for this one, we have two channel RG, so we might need to split it up. So I can do it with channel mix, or there are other way that you can do it easily as well. So I take the red channel by putting 0 elsewhere, so that we'll have the okay, yes, only red, the rest is 0, so that is the x value here. And the second channel mix, we are going to find the y value. So there will be no, but only the green value here. And also we keep it single. Yes. And then we choose the function with arctangent 2. And the output is in degree, so you just have black and white because the value of degree is pretty high in comparison to 0 to 1, but of course you can see the actual value from here. So that is the calculation, but if you want to change it to radian, so that is a little bit more intuitive in a sense that you see the gradual change of the angle information. Since we're going to use degree for the calculation, we keep it degree first, and then this one, yes, single channel, and then we'll send it to the output. Now we are done with the angle here. So that is the first part. So the first part, we calculate the distance from any point in your optical flow bounding box towards the center, which also explained from here. We use the RAM for calculation adding, and then with this we split into the distance and the angle. So now come to the difficult part, is the here. So we more or less settle this triangle with the fixed information. So we are going to do this one, x2, y2 and x1, y1, which is maintained in our optical flow information right here. Yes, along here. So we send it here, which is this input. So this input again also come with two channels. So in this case, I can send it to a resolution and then try to just keep the red and green 32-bit with this one. Yes, with the optical flow information of the red and green two channel, and then I'm going to split it into magnitude and angle again. So in magnitude, I copy and paste this one. Instead of sending the RAM information, I send the optical flow information to here, and then you can actually send it out to a null, and then to display the pixel value, so you can see the response by moving your body. So that is the magnitude information. And the second thing you can put it will be the angle information. Yes, that is the angle information. It's a little bit more chaotic because the value actually returning from here is a little bit large in comparison with the magnitude. So see the value of your angle display. So now you have everything of this diagram. You have the angle A3, you have angle A1, you have the distance D1, you also have the distance D2. So next step is to do the calculation. It's 90 degree minus A3 and A1. So what is A3? A3 is the, I can just put it as a null with the proper name. You can see it a little bit more clearly. This is D3. So this is A3. Yes. So the distance of the optical flow is this one, D2. So I put a null called D2. And then the angle here is A1. And that one is the distance. We call it D1. Okay, so the difficult part is we're going to do 90 degree minus A3 and A1 as shown in this diagram. So first we do the A3 minus A1 first. So we have A3, we also have A1, and then we're going to do the minus calculation. So that can be a little bit tricky, so we need to combine the two images first by using a reorder. The A3 in the first channel or first input, and then the A1 in the second input. So since everyone only have luminance, so the A1, A2, the input 1 and input 2, choosing just the luminance. So we now have two channels, red and green, with two channel information. So this is the one we combine the A3 and A1 together with the A3 in the red channel and A1 in the green channel. So now we are ready to do the minus in the mask. So we are going to combine the channel by doing subtraction, and we only have red, green, and the final output is only single channel. Okay, so that is the A3 minus A1. Okay, and then which is single channel. So the next step we're going to do is to do the 90-degree minus itself. So in this case, we are going to multiply by -1, and it's actually we swap the polarity, and then after the minus we add the 90-degree. So now we have the final result. I can just put it at the variable we use is A4. So we now have the channel right here, and we also have the two distance. So what we are going to do is to combine them together by doing the calculation. So we need to do is to D2 times the cosine of A4 and also D1 in order to finish it up. So we are going to do the cosine. So we have the A4, we add the function, and since only have one channel, we do it in the red channel. We do a cosine with the value of degree. So we have this cosine function, and then we would like to multiply it with D1 and D2. So again, we need to combine it into one single image first. So the D1 we go to input 1, and then we have the D2 go to input, D1 input 1. It's actually the order doesn't matter. So I just want to keep it tidy. Okay, so we use input 1, 2, 3. Input 1 we use the luminant, then we input 2 also the luminant. And then the output will be RGBA, but the A I just keep it 1. Okay, so this is the result that we want, and the final one is we would like to multiply them all together, input 1, 2, and 3. So we are going to do multiplication by combining the channel, and then the output will be one single channel. And if you want to, you can also skip the alpha, but it doesn't matter. So we would like to output in a single channel in this case. Multiply RGB and then output, yes. So the resulting image can be quite small because of the optical information. So the next step is we do an average analysis of all the pixel values around here, full image. And then we convert it into chop by taking the full image pixel and output one single channel set. And since we only have one value, so we just take out others, and then I rename it as angle. So you can see the value is very small. So in this case, you can consider to multiply it to a bigger value. So actually, you need to be quite big. In my testing, I used 10,000 to see if it's big enough. And you might also want to do a filter to smooth it a little bit. So that is the final calculation, and the calculation you can send it to the output chart. So now you have more or less everything ready in this new component called float rotation. So by implementing the complex formula and to single out the number for rotation driven by the optical flow, and then we come to this critical moment to do the testing. So this one you no longer need, so you can just remove this one, go back to here to initialize again to do some testing. So I can just move it to other location and then to do something like this one. So probably this area will be a little bit easier. So you can see the movement. So if I turn my finger like this one, it's actually rotating this. So the magnitude is not too much, so in that case you can consider to increase the mass value to see if it can respond better. So that is the rotational effect, that since I use only 2 fingers, so again the background is not too much different, so the response is a little bit less significant. But you can see the operation is the movement of the 2 finger actually rotating this ball. So it's also I can use other objects as well. So, but it seems that the horizontal movement is a little bit too significant. So in that case, I try to reduce it a little bit such that I can hold the objects. So now the movement is less significant, but you can see the rotational effect. If I have this one, that you can see it a little bit more clearly. Okay, I probably can also add a little bit to the rotation response such that you can have a more dramatic result with this one. Yes. I try to do it with my head. Okay, probably you might have better result with a bigger board like this one. Then I pause this one to a bigger one, and I can resume it to have a bigger translate value. So you see more or less the rotational effect like this one. So in the result, it combined two effects. One is the translation, and which detect the overall movement direction and magnitude of the whole area. And the other is the rotation effect, which kind of detect the optical flow around the center of your virtual objects. So that is the thing that I prepare for this exercise. So the sum up is this version is the last one we have done in the last tutorial, except that we add a new component which kind of implement the two formula that I'm going to show in the page on. That's the calculation of the distance and the angle. And by taking the product of the three area, one is the distance of your optical flow and the distance between the point to the center, and also the projection along the perpendicular line, and use it as an estimation of the rotation. So this is done in this particular area that can be a little bit more complex, and the flow one is a little bit more intuitive. So that is the thing I prepare for this. So in the Patreon I'll put the video, but in the for the project file I'll probably put it in a new Patreon we need to pay because it's quite complex and sophisticated. So that is the arrangement, and I hope you can enjoy this link-free tutorial, which more or less conclude the exercise we work with optical flow and interaction design in this series. Okay, stay tuned for the next one. Bye bye.